All right, and now 5.4. 5.4. Self-inductance and simply inductors. This is really where we're all building towards. So the cool thing about this whole concept of inductance that we've been describing is that it also applies to itself. And you may have kind of started to think that here, right? If you're changing the current, you're changing the magnetic flux not only through this loop down here, but you're changing the magnetic flux through the original ring that's producing the magnetic field and the magnetic flux in the first place. And so you get that Lenz's law, that Faraday's induced EMF in the original one as well, and that's called self-inductance. And so this isn't a thing that is powering itself. That's the wrong way to think about it. It's a thing that's resisting itself. It's like a laziness to get going. It's at any change, there is a resistance to that change. And so it's not like you're getting energy for free. That's not really how to think of it. Whenever you see like self-something in a physics concept, you might think it's a bunch of hooey. But this one, it's really just the opposite. It's resisting what itself is trying to do. So if we just have one loop of wire and we change the current running through that wire, then we have also changed magnetic flux through itself. And there is actually a self-induced EMF in that top loop here to counteract this change in flux. And since it's in opposition to the change in EMF that we just inflicted, or change in current that we just, turned a knob to control, then the induced EMF on that top loop here acts as a brake to any current change that it itself undergoes. So it's really weak in just a single loop, but we can multiply the effect just the same as with mutual inductance. We can multiply the effect of self-inductance with every additional turn in a coil. So for a coil with n number of turns, the self-inductance, which is denoted by a capital L of a circuit, is given by this capital L, big and bright, wow, there we go, being equal to number of turns times the magnetic flux divided by the current, right? This is the same thing, it's just not referring to something from something else, right? So this was referring to the magnetic flux through itself according to its own number of turns because of the current in the other one at any given moment. Well, now it's the number of turns. We don't have to specify one or two because it's itself. It's just one ring and we're changing the current, and so therefore there's self-induced EMF to resist that change in current because of specifically a change in magnetic flux. And so you have number of turns of itself, no need to specify, the magnetic flux through itself, no need to specify, and the current that's going through it itself. There's no other thing here, so it's a little bit cleaner of a formula. And when it's clear from context that we're not referring to mutual inductance from some other loop that's being driven, the self-inductance is just shortened to simply inductance. So, inductance. And that's because it's so ubiquitous. We don't, self-induction is so ubiquitous in circuits that we don't want to refer to it constantly as self-inductance. It's mutual inductance that actually is the less common one that we should specify. So when the current in a circuit changes, in other words, there is a self-induced EMF produced by the circuit, and that is given by minus L delta I delta T. And you'll notice this is basically analogous to what we were saying up here, right? M delta I1 delta T, that's the induced EMF in the other, the second, right? But now it's on itself. And so we have this new thing, L, which is a more simple looking thing because it doesn't involve two different quantities, it just involves itself. And we have this equation that doesn't refer to, well, the time is the same in each, but it doesn't refer to the current of some other one to give the EMF on the first. It's its own changing current according to its own number of turns, and the magnetic flux through itself according to the current that it is currently experiencing of itself being equal to its own induced EMF. All right. And again, this minus sign in all of these is indicative that the self-induced EMF is in opposition to the change in current in the circuit. Same concept as what Lenz's law is trying to distill for us. So this is self-inductance. It's ubiquitous because it's can be incorporated as a circuit element. So just like we have a resistor, or a voltage source, or a capacitor, right? We can stick these on a circuit and have them do certain things. Well, we now introduce inductors. So inductors as circuit elements. So this is the coolest thing ever because they're not any other kind of weird material that is being used. There's no, in a capacitor you have to have like certain plates involved and you have to have some sort of dielectric in between. It might be air, but there's some sort of architecture involved in this. And for a resistor, usually they come in this pill form that has some, material, and it's got stripes and colors, and it's this thing that you have to buy. An inductor, you can incorporate inductors discretely as little components that you add on because they're engineered for very specific inductance, capital L, right? But they're the most simple thing ever because it's literally just the wire of the circuit coiled around, right? Some amount of times. And so based on just the wire being bent a certain way, you've now invented a new circuit element on your circuit. It's the coolest thing ever. You can take a circuit that's like this with just, we'll say, some battery or something, and maybe you have like a resistor, right? A resistor, and maybe over here you have a capacitor and blah, blah, blah. Well, now you can take this circuit, which existed like this with a resistor and a capacitor, and you can, if you really wanted to do it rudimentarily, you can take the wire and just bend the living heck out of it into a loop, and now you have invented a new circuit element, an inductor, and it serves as a giant brake on the circuit. So if the current changes dramatically, then it just kind of resists this. And so the times where this is used is partly to spare parts that can't experience such a rapid change in current. It would damage them to do so, maybe. And so you stick an inductor on there, and it resists this fast change in the current going around a circuit, acting as like a brake. So anytime something happens, it kind of just comes out with a little whistle, a whistle and a stop sign. It says, hey, 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 slow down, slow down, slow down. It kind of just resists the change. That being said, this is a resistor, and I keep using the word resist in terms of an inductor. There is a clear distinction here, and I want to emphasize that. A resistor resists the flow of current, right? The flow of current. Even if it's a steady flow, the resistor provides some restriction on that flow. An inductor doesn't care about a steady flow. It doesn't care if the current is 10 million amperes, which is insane. It doesn't care if the current is 10 nanoamperes. All that it cares about is how fast it's changing. And so an inductor blows its whistle and starts a back EMF in the reverse direction to slow down the change when a change in current is experienced on the circuit. So it's pretty cool, and it serves its own function. So a resistor resists the flow the current. An inductor, quote unquote, resists or induces a backwards reaction, which opposes a change in current in either direction, right? You can flood the circuit with current in the self-defined positive direction, or arbitrarily defined positive direction, or you can decrease the current a bunch, and maybe that would damage a component, or maybe that doesn't do what you want it to do. And that would, the inductor would then push forward a little bit of current to just kind of decrease how much that's changing, right? All right, so now I kind of just said it here, but like the circuit symbol for a resistor is like this, circuit symbol for a capacitor is like this, circuit symbol for an EMF is like this being the positive side. So we have these different symbols. Well, now we introduce a new one, and it's this, because that looks exactly as the most basic version of what it is. And that honestly is what they look like. If you look at some circuits that aren't microscopic, so you can't really open up your phone as easily and see these. But if you were to look at some circuits, you would see these little coily components. They exist, and they are inductors. So let me skim my notes and see how far ahead I got and what I skipped that I want to make sure and say. I think I said everything in that little section. So we're going to now talk about the energy that's stored in an inductor, because a discussion on energy kind of elevates this discussion a little bit. So energy in an inductor. And I just think these things are so cool. So say we have a circuit with an inductor on it and some other controllable EMF source, right? So maybe this circuit like right here, right? But with no, well, let's not get too far. Let's say it has no other thing. It like literally just has an inductor on it. Otherwise it'd be a specific circuit that can be analyzed in more depth. Say we turn up the voltage on this EMF source, thus increasing the current through the circuit. So we increase the potential difference here, increase the EMF, and so then the current increases around the circuit, right? So increasing, right? So we know that what the inductor is going to want to do, it's going to want to resist that, right? So we increase the current through the circuit, and then let's say we leave it steady and it reaches some desired current, right? And then we reduce the voltage back down to 0. So now there's nothing. And the way we do that down to absolute 0 maybe is remove that altogether. Or let's say we have it connected to a box in which we're just turning a knob and we can actually turn the voltage all the way down to 0. And so in that decrease process, we are decreasing current, and thus we're decreasing the magnetic flux, right, through this thing. So if the current, just to go through it real quick, in this form, if the current is this way and it's decreasing, then the current is decreasing in the forwards direction, right? And so we need the magnetic field to be going through this way to reduce the induced magnetic field. I'll do it in that same purple color. The induced magnetic field would be in this forward direction because the magnetic field is decreasing, even though it's still in the forwards direction, it's decreasing in the forwards direction because the current is going down, and so the magnetic field strength is going down, and so the flux through that inductor, all of its turns and coil, is going down, still in the forwards direction. So we need to send more in the forwards direction to kind of attempt to bring it closer to where it was a moment before when the current was higher. So the magnetic field is in the forwards direction, right? And that induces a little bit more current to flow in this forwards direction. So we've decreased the change in the current going down. So the current would have gone down just strictly according to how much we turned the voltage down, V equals IR. But now we've added a new EMF source, right, over here because of the inductor, and we've now introduced this new temporary induced current in the forwards direction to minimize this change that just occurred. So this all kind of sounds like a potential energy that is stored for a moment, right? When you increase the current, it resists that, and it's kind of like it stores something. When it increases it, it steals some of it away, and it stores it in some form or another. And then when you decrease the current, it expels that energy in such a way as to smooth out the change, right? It's like inductors are like little harmony mechanisms on a circuit. And if something, if things are getting a little intense, then they kind of siphon off a little bit of that intensity. And then when things are kind of starting to dry up, and then they kind of let that energy flow again. Hopefully that kind of seems intuitive to you, as it does to me. Otherwise, I'm just talking nonsense. But to analyze that process specifically, we see that there's some sort of energy stored. So where did the excess energy go that got kind of siphoned off of the circuit, right? So the current is increasing in the first part. The inductor kind of siphoned off some of that energy and presumably does something with it, right? And it has it later to then release to the circuit. And so it's not expelling it in the form of heat like a resistor might. It's not expelling it. It's storing it in a potential form. So in some cases, this release of stored energy in the inductors of a circuit can be quite strong. And that may be because the number of turns in the inductors on the circuit are very large, or there's just an immense change in the current. And sometimes it's large enough that it causes enough of an EMF in the circuit, say like when the current is just from a very high value just completely shut off, then this stored energy in all the inductors in a circuit, if you imagine a whole thing like maybe a space heater or something, they release all of their stored potential energy. I guess you can say inductive potential energy, although I haven't seen that phrase written in textbooks. It releases it all, and it's possible that you get arcing from your circuit to the nearest low potential because there's so much current that's trying to flow, but now it's no longer a complete circuit. So it's just sitting here at this like huge potential difference, this huge EMF on the circuit, and it'll just find the lowest potential nearby. And you may have seen that before when you take a large wattage appliance like a space heater on full blast and you just unplug it as it's running, or even like a large lamp or something. You unplug it while it's working, you'll see like a little arc from the plug back to the wall because all the inductors that are there just resisted or tried to diminish the change in current that just happened and send some current through. To go from full blast to nothing, it reduces it a little bit by sending a little current through in the same direction that it was going, but you just unplugged it from the wall, so that current kind of just jumps the gap there, and it causes that arcing. And that arcing, by the way, is the same thing as lightning. It's just obviously there's no induction occurring on the climate scale, but charge jumping from high potential to low potential in whatever means it needs to, if it's a great enough potential difference, that's lightning. So the same kind of effect that you see when your finger has a certain charge built up, static charge, and you get a static shock on the doorknob or something, that's mini lightning. It's the exact same effect. It's just tiny, tiny lightning. All right, anyway, so back to this stored energy. It turns out that the potential energy stored in an inductor can be written as, so I'm going to write U-I-N-D for inductor is equal to 1/2 L-I squared. Now, does that not feel satisfying to you? This is how many times over and over we keep seeing the same forms for energy, right? Yeah, 1/2 mv squared, 1/2 kx squared, right? So, and then we had our capacitor one as well, which was also in a similar form. And so it's really interesting. So in this way, we can kind of see an analogy to other potential energy forms. And I'm going to liken it to a spring. So the inductance of an inductor can be likened to K, the spring constant, right? So like U elastic is equal to 1/2 kx squared. And the inductance, L, of an inductor can be likened to the spring constant. It's according to the properties of the spring, compressing it at a certain amount stores a certain amount of energy, right? And so same thing for an inductor. According to the properties of an inductor, right, sending a certain amount of change in current through it stores a certain amount of energy. And then I can be likened to how much that spring is compressed there. So it's really, really interesting, these similarities that you see in physics. Yeah, and beyond that, by way of analogy, we continue to see the same basic physics show up in more and more complex domains in our universe. So these aren't little tricks, these aren't like little teaching faux pas. This like really literally is analogously very similar. And it's little wonder why physicists have been pursuing what's called the great theory of everything, or TOE, right? TOE, or grand unified theory, GUT, G-U-T, for decades. And the further you go, the more examples you see that seem to indicate that all the phenomena in our universe may just be one single phenomena witnessed from different perspectives, right? Electrical, mechanical, gravitational, all these different things. It just feels more and more the deeper that you go that they all ought to be described by one single thing, because they are all acting analogously, very similarly. And it just seems like there's just one single thing that's just being seen from different angles or interpreted in different contexts. Sort of like if you have one object in the center of a room and you have a different light source, right, in different directions, then it will cast a shadow looking however it looks from that light source in that direction. But if you could have the dimensions to see, or the ability to see the object in the room, instead of just looking at these shadows, right, then you might see that it's all one thing just being interpreted from different spaces, different perspectives. Anyways, all of that is a little bit speculation, but it's one of the reasons why I continued to fall in love with physics, because it just makes so much in the universe around me interesting, and I hope it does for you too.